Hello everybody, welcome to part 8 of the Openthread 101 series, and in this video we will have a bit deeper look into the mesh link establishment protocol. If you remember, in the last video there were several packets, or almost all of the packets that we saw were mesh link establishment, and it's because this is the protocol that is used to manage the mesh network within Openthread. And since we were not generating any user traffic in those videos, all the traffic that we saw were coming from this protocol. And today in this video we will try to take a deeper dive into it and understand what this is all about. Just to give you some reference links, the first useful link would be the network discovery information guide from Openthread, and it gives you some information about some basic information about mesh link establishment protocols and what happens when a network is formed or what happens when a network is joined by a device. Then the second useful document would be the second two most useful documents would be the Openthread specification. It can be downloaded from here. So once you enter your email and information, then click the submit and they will send you the specification. It might happen that they will not send it, then you can try it again with a different email and maybe then it works. And then another document is the IEEE 802.15.4 specs. So when you are reading the Openthread specification, they would often have references to the 802.15.4 specs, and then I suggest that you have that document handy as well, and you can download it as well from here. You can either just use this link, so it's a Git program from IEEE that gives you access to some of the specification, or you can go to the Nordic documentation. So if you go to the 802.15.4 page in the Nordic docs, here you will see this link that here you can then create an account and download the 802.15.4 2020 specifications. I have these specifications downloaded, so this is the IEEE 802.15.4 specification. I have it open. I was reading something here, and this specification is 800 pages and there are so many chapters. This is the latest one, but I would suggest that you have these, and when you need to look something up, then you can look them up in these specifications. Another most important document, which is even more important than this one, is the Openthread specification, and I have it here as well. So the specification for thread 1.4, it's also some 625 pages and divided into several chapters, and you can also look them up. Just since we are here, the mesh link establishment is a whole chapter here in this specification. So this is really the place to look for anything related to mesh link establishment. And here you see as well that they say that the initial MLE framework was defined by the IETF draft, and this draft was let me copy this link. Okay, let's see if I can select it and copy it now. Okay, so IETF, we can just search Google IETF mesh link establishment protocol, and here is this guide. Yeah, so this is probably the latest one then, and this document also gives some information, but this is the base, you can say. This is the base for mesh link establishment protocol, and if you go through this documentation, it says the mesh link establishment framework must be implemented by the thread interface, and it says the initial one was this one, but then thread interface must implement the MLE protocol specifications described in this specification. So this document is the most up-to-date reference on when it comes to MLE. So let's this is enough for the PDFs for now. Let's just start sniffing, and then what we would do is sniff our network formation. So we would turn on one device, it will create a network, the sniffer would be on, then we would turn on another device and it will join the network. So let's open Wireshark, and here we have the sniffer, so already set to channel 14, so that is all right. So let's just start sniffing here, and currently we won't see anything because both of our devices are offline. So let's bring up their terminals, and these are the terminals. So device 1, device 2. So let's just do it quickly. So OT dataset active. So this device has all the information about a network, and this device also have all the information about the network. So what we do is OT config up, and then OT thread start. So basically now this device is started. It is sending some link requests, so trying to establish links with any router that are within its range, and the protocol you see is MLE here. And after some requests, if it does not receive any response, then it will switch to sending parent requests again. This is typical. It just wants to find devices that would accept him as a child, and it's a bit funny. Here data requires, and then here it is advertising. So once it starts advertising, that means it is now part of a network, or it created a network. So if you do what is state, now it says it's a leader. So now we would bring up this second device. So we do OT config up, and then OT thread start, and then we would keep checking OT state. So currently it is detached. So now you see here the F4 IP, and we have a 6D IP as well here, a new one. And here these devices are talking with each other and doing some stuff. So if you now look here, our device is currently a child. So every device joins as a child, and now after a while, since our device is the second device is also router capable, it will become a router. It would request the leader to create make it a router, and we will see that request also very soon. So it still haven't made a request yet. Maybe it doesn't want to do it. Let's see. Okay, so now it did something. So basically it is asking, okay, so these IP addresses you can find, these are a bit strange, but these are also IPv6 addresses that are used within Openthread. So what we see here is that we stop the sniffing here now because that's what we needed. So what we see here is that one device with the IP address of FDB5 and then all the way to 2003 is asking a device with the IP ending at 200 it's sending some UDP packet, and then the device responds, and there is also acknowledgement. So it sends a packet, and then this device acknowledges it, and that's the IEEE 802.15.4 acknowledgement. You can have a look at this in the specification if you want. Then another device respond from the router, and then this is basically the way it happens. This traffic is basically CoAP but currently we haven't it configured, so the CoAP standard port is different than 61631. Openthread uses 61631 port for CoAP to do some network management as well. So once we configure, then you would see what this is, but let's just make sure our second device is now a router. So that's how it upgraded itself to become a router. And if we want to have a look a bit more into this traffic, then we go to the protocols, and here we would go to here. Okay, and then the UDP port, so it's currently 5683. So we would have to do is 61631. I don't know if we can, yeah, probably we can specify. So let's just don't replace the previous one. Let's do it again. Go to protocols, because if we do replace the other one, then it would not detect the authentic CoAP traffic as well. This is, so we would copy it maybe, and then we do is 61631 and apply, and okay. So now here we see that this is these requests are CoAP requests and constraint application protocol, and if you look here, it has the URI and all that stuff here. And if you want to look a bit more into details into what is going on there, maybe we can have management and CoAP, and here you can see that some what it uses. So in CoAP message format, mandatory options, and whatever, but it uses CoAP to make some communications between nodes as well. The difference between where CoAP is used and where MLE is used. MLE is just used on the link local, so it's not used on the mesh level. It's only used on the single hop level, so it's just broadcasts and single hop level traffic. And that's why if you see here, the communication between these devices are also using link local addresses, because this traffic would not be routed. And for the CoAP, it's communication between a device and the leader, and the device can be several hops deep within the network, and it has to communicate with the leader, because the leader is the one who approves router requests and things like that. So then they use the different IP addresses which are mesh on the mesh level. Related to these IP addresses, if you look to your devices and we do OT dataset active, no, that's not the command, OT IP address. Here you see that we don't have an IP address on the device 2. We have the IP address was 2003, and FDB5, the requesting device was F003, and we know that this was this device here, but it doesn't have this. So, and then another one, if we do OT IP address, here we see that this IP address is here. This IP address is, I think, called RLOC, so route locator, and it is, we would go a bit more into details, but basically this IP address is based on where the device is located within the network, so to which router it is connected, and that way it is easier for devices to send packets to each other if they know each other positions. So in some cases, like in this case, the CoAP is using the RLOC IP address, but in general, in our applications, we would use this IP address, which is the mesh local IP address, which is this one here, and this one is the link local IP address for both of these devices. Yeah, so now let's come back here to the protocol, the link request command. So just because here you see link request, parent request, data response. So if you go to the document here, it says when creating a new thread network or searching for an existing one to join, a thread device performs an active scan for 802.15.4 networks within the radio range. So it performs an active scan. An active scan means is that it's probably sending something. It's not just listening. And what that means is it broadcasts a 802.15.4 beacon. And then in response, another device also sends a beacon, and basically the new device sends beacon, and the routers responds with beacons as well. That includes their PAN ID, XPAN ID, and network information. And that means the device then knows, okay, I can, if I want to join this network, if it has the credential, then it can join this network. To be honest, this level of details is not so clear to me as well. Also, if you, let's say, have a look at this beacon here, I was searching for this beacon, but I did not find it. So if I look at 802.15.4, if I go to the specifications here and make frame format, and then frame formats, these are how the packets are looks like. And if you look here, frame types, right? So in the frame types, the frame type for the beacon should be 000. And if you look at the packets here, right, this is the packet, this is the frame. So basically not here, this is basically what it looks like on the wire. But the IEEE frame, this is the IEEE frame. We are picking this up from the IEEE 802.15.4 specification, and the type should be 000 for beacon. So if you look at here, this type is 1, which is data, and Wireshark also tells us that this is data. Now if we want to look if there is any device that has this field, any packet that has this field set to 0, that would be basically a beacon, right? So if we search here, you see nothing here, so there is no beacon. So what I get from this is either this document is not so much up to date, or Openthread is no longer, or Thread is no longer using this beacon, this 802.15.4 beacon. It is using this MLE protocol to also do the discovery. So why do I say this? Because here you see these advertisements, and devices are basically finding each other using these advertisements. And if you look here, let's look at the link request. Link request is it's a MLE packet, and this is IEEE, so this is not where we would find MLE related information. We would find them in the Openthread documentation, so mesh link establishment, and then we have these are different MLE, but what we have, if you look at the Wireshark, right, so we have the IEEE frame, which says it's data frame, and then the 6LoWPAN is some kind of remove some compressions and stuff, so that's why now it's IPv6 packet. Then UDP, not much useful, all of these are just headers, and then the actual information is contained here in the mesh link establishment. So this is just the device got online, it is sending a packet with a link request, and that link request is a IEEE data frame, IEEE data frame that is of type data, and it is also including some MLE information there. So it's this MLE information is encrypted basically with the network key or some kind of information derived from the network key. And here it says what it is. So here in this type now, the MLE type, the type is link request. So any device who can listen to this device, if the listener device does not have the network key for the network, then, or for the same network, then he would not understand this, because this information is encrypted. So if I go there, go to preferences, protocols, and go to 802.15.4, and this is the network key. I copy this so that I have it, and then I remove this from here. Okay. And now you see here that in the mesh link establishment, so all the information up till here is open. We can see that, but here the mesh link establishment, it has some data which is encrypted. And how do we decrypt that data is because there is this something called auxiliary security header. And this auxiliary security header is basically, it contains the information how this data is encrypted. I don't entirely know how they extract the key from this, but I think it is, if you look at the specification, so for mesh link establishment, probably there is some network attach, child link, neighbor link, processing, security considerations. General has the strength and weakness that it inherits. The one exception, operation requires accepting and acting. Somewhere in these documents it says that if you look here, maybe somewhere here, thread device security formats. So here, this is basically what we need here. So it says that the MLE is used to initiate link layer security. So when the devices are basically starting to talk with each other, there is no link layer security here. So basically everything is plain. But what it does is it uses, the MLE is used to establish security on the link layer. And where was it? It's here. This means that MLE itself cannot always rely on link layer security. So MLE basically then uses encrypt its own payload, and it uses the encryption that is defined in the standard of the 802.15.4. And here this says it's as a result, MLE message have the following UDP payload format. So it's if the starting is 0, that means this payload is encrypted. If the starting is 255, that means the payload is not encrypted. In our case, it says 0. So if you look here, it says 0 here. That means the payload is encrypted. If the payload is encrypted, then the next one is auxiliary header, and this is the auxiliary header. And the auxiliary header then has 3 fields: security control, frame counter, and key identifier fields. Security control then basically gives some additional information about what kind of security or encryption is being used. Frame counter is then basically to count frames. So it's like this one is 655. 656 is the next one, 657 is the next one, and so on. And the key identifier field then contains information about the key. So I don't know if this is the exact key that is being used, but I don't think so. I think this key is used as in combination with the network key that we just removed, and some magic is happening here to decrypt this. And if you look here, here it says 10 key identifier mode, explicit key with 4-octet key source. So it says explicit key with 4-octet key source. Probably that means that so here, if we look here, command for no, okay. So this is basically, it says this auxiliary header is not something that is defined by Openthread. It is something that they just uses it. So they just use something that was already defined by 802.15.4. And if you look here somewhere, there is auxiliary. If we search here, auxiliary security header field, maybe there's let's search this. Probably there's this looks like a very small subtopic. So auxiliary security header, yep. So it says auxiliary security header has 3 information, so, or 3 fields. So security control, then the frame counter, and then the key identifier. And the security control then specifies which kind of security level do we have. So this is the security control. So security, we would just have a look at this like this. Okay, so security level, so it says 32-bit, then key identifier mode, and key identifier mode, so this is what we are interested in. So let's go to the security level, and then the key identifier mode. So the key identifier mode field is an unsigned integer that indicates whether the key that is used to protect the frame can be derived implicitly or explicitly. Furthermore, it is used to indicate the particular representation of the key identifier field. So basically, I don't want to go too much into details here, but here in our case, this is 10, which means this one. And it says the key is determined explicitly from the 4-octet key source field and the key index field. Now, I don't know what they mean by explicitly, or I don't know what if this document contains another more details into the implementation of this, but the crux of the matter is that this mesh link establishment protocol is encrypted, and then they have this auxiliary security header. And although it's currently on the top of the UDP, once we have link layer security established, you would see this header here as well. And maybe in the future, then I will show you why. Once you have the link layer security established, then this header would be here, because this is the actual position where this header belongs. But since at this stage there is no security established at the link layer, Openthread uses mesh link establishment protocol to provide a secure channel for link layer security establishment. I hope that was a bit understandable and not so much all over the place. And so this was the what was going on with the security header. Let's then set up the key again so that it can decrypt. If you know where the logic for the decryption, because this must be okay, no, that's not the right thing we need this key here. So we go here, we paste it, and then here we have to select thread hash. Okay, and now we have some information is now decrypted. So link request then contains fields that are defined also in the documents. So link request type have some of these TLV. Parent request type has some of these TLVs. These are type, length, value fields. So if you say that's the first character or the first field is usually the type, then the length, how many bytes it is, and then all the data. So here the type is challenge, length is 8, type is 14, length is 1, type is 18, length is 2, and then this one. If you look here now, the parent request, and let's see, let's have a look at the, so let's look at the link request first. In the, not in the, it should be in the Openthread now. Security format, command format, link request, a request to establish a link to a neighbor. And then we have all these different types of packets, MLE packets that are doing different stuff. And yeah, you can basically go through them to figure out what is going on here. Here you have the types as well. So these are basically the type of the MLE packet. And here the child request, child response is coming here. So these details are also mentioned here. So from this document, like I said, I was not able to find this beacon, but I think it uses the mesh MLE to establish a secure, and it says MLE only proceeds once a thread device has obtained thread network credential through thread commissioning. So the device, both of the devices needs to have the network key, and then MLE can continue start operating. Once what happens when a device is joining a network? So this is basically this process. So from here, our device is child sends multicast parent request to all neighboring routers. The neighboring routers sends parent response. Child chooses a parent device and send child ID request to it. The parent sends a child ID response, and what information they contains, so scan mode and things like that. The parent response contains version, response, frame counters, MLE frame counters, source address, link margin, connectivity, leader data, and then, so these are parent request, parent response, then child ID request to each device. So there is a router ID and there is a child ID, and each device needs a child ID for it to be then get IP addresses and things like that. And if you remember these addresses here, this one, I think this 20 is the, or either 02, whatever, but this contains a router ID and then a child ID. So in the router ID is 20. Since this device is a router, then the child ID for this device is 0. And if you look here, the source address is 2003. That means the router ID for the device that was connected was 20, and then the child had the ID of 03. So this is the process where this device is trying to get this child ID. And if you maybe we will see the 03 ID here in the response. Let's see. So child ID request, it means it then exchanges some information, address registrations as well, registers an IP address, and the response is usually the source address. So the parents are log16, child's are log16, or log16 is the ID basically. So let's have a look at this side by side. So this is the child ID response, and here we have the child ID response, and it contains the source address is destination extended source address is 2000. So basically this is the source address, and then there is an address 16, so 2003, it gives this child the 2003 ID, and then we see here that the child is using that ID to send a packet here. Then the leader data, some information related to the leader data, network informations. So if you look at the network data here, probably it's not a lot, because our device already have some of the information about the thread network. So it's on mesh prefix, address, auto configuration, more specific routes, and then route 64 is read only. So I guess this is only shared if the receiving device is router eligible, and then it gives it some kind of routing table. There is a timeout here somewhere, active timestamp, and address registration. We don't have, but I guess some of these entries are then dependent on whether what kind of device is trying to connect and things like that. So this was the attaching process. So if you look here from the start, link request, and there is a parent request, parent response. I don't see a link accept here, but maybe it is not done here. I don't know, because if you look here into the thread TLV formats, TLV command formats, there is a link accept as well. It's a link request and then link accept, but here we don't see it. If you look here, let's see, link request is the field. So this is the field here. So if you filter, no, not that. So let's just do that. So these are all the link requests, and if you look here, link accept is 1. So link accept is 1. So let's just type to see if there's any 1. No link accept. So maybe it's just not used, it's optimized out, or we just didn't happen to come across it. It's usually some kind of optimizations happening where if for example here we have a link request, and it already saw an advertisement, so maybe now it already know that it can establish a link, so it just directly proceeds with the parent request, and then once the device is attached, it stays a bit for a while, and then it requests itself to be promoted to a router, and then it becomes a router. So this was one way of doing it. I would save this file so that we have just save this as a reference. I have this here as well, but I've replaced this. And the second scenario I want to go through is so if you remember, when we were bringing this device online, it had all the operational dataset information it needed, but the only required ones that we need are the network key. So what we would do is create the network. No, stop, not create a network, stop the sniffing. Clear this so this device stays online, and we would do is ot-ifconfig down, so ot state is disabled, and here ot state here is leader. Now we are interested in is how this device, if it has just the security key, how does it joins the network. So I expect the device 1 to share some information like the router name and the network name and PAN ID and things like that in a MLE packet. So let's do that. So what I would do is start sniffing, and then what I would do is OT dataset active. So this is the dataset that we have. I would copy this. OT dataset is just the network key now. So we don't have to do anything here, but if your OT dataset is like this whole thing, then what you can do is, let's do it OT dataset clear, and then if we do OT dataset or dataset is empty, then we do OT dataset network key, and then we paste the network key. And if we check the dataset again, OT dataset, it is now just the key. So we do OT dataset commit active. Wow, that's a lot of requests from the device trying to figure out where our device 2 went. It is just listening, sending link requests after link requests, and now it's just okay. So it just flooded. I don't know what was going on there. Let's restart this again so that we don't have those traffic. And OT dataset commit active, and then if we look at just the active dataset, just that. So we do is ot-ifconfig up, ot thread start, and let's wait until we start seeing some packets so that we are sure that our capturing is working. Okay, so our device 1 is advertising, so device 2 do a link request, another link request, another link request, and then link request another one, and then it sends a parent request, and device 1 responds with a parent response, child ID request, and then there is a something going on here. So the child ID request was done, then there was acknowledgement, there is another packet that is sent, but there is no child ID response. Maybe it got lost in the OT state, so it got lost somehow, or all the packets were probably not captured, and the only packets that were captured was this one, but we don't know how to decode it or whatever reason happened. So let's stop. Then we do is ot-ifconfig down, and then OT dataset active. So now you see it has received all the data set, all the information, but we were not able to capture it here, and that's what I want to do. And let's redo this again. So our device is, let's have a look at our pending data set. So what we do is we would OT dataset commit active. So this will make our pending dataset the active one, and since it only contains the network key, so our active dataset is now also contain only the network key. So let's start snipping again, and what we do is OT dataset. Okay, so it's already active, so I've config up OT thread start. Okay, the child ID request, and it's still child, but what was happened was, this is the router stuff. Okay, so maybe we need some kind of traffic before. Let's do it like this. OT if config down, OT if config down, then start sniffing, and then we do OT if config up, OT thread start, and then we do is OT dataset active, OT dataset. So both are fine, so we will do OT dataset commit active, and then OT just to ensure. So now our active dataset only contains network key, so we will do OT if config up. So we bring up the interface but haven't started the thread yet. OT state, currently our device becomes leader, so we do is OT thread start, and now our device is making a link request. They should exchange some information real soon. Parent request, child ID request, acknowledgement, advertisement. So it did a child ID request, and we were not able to capture the child ID response. So information about the thread network, or I don't know why were we not able to capture that. Maybe is it skipped out somehow, or what is going on here? So it is acknowledging something, sequence number 62, sequence number 158, 150, 125, and then it sends an advertisement. There's the no extended source address, can't decrypt. So here it says no extended source address, can't decrypt. Security header is 32, key identifier, key index 01, key identifier mode is 01. That means 01 is key is determined from the key index field, and in the key index field this is 01, and warning undecoded, can't decrypt. Yeah, so there's something going on, but in this case Let's retry it again, maybe works this time. OT if config down, OT dataset commit active, OT if config up, OT thread start. There is a link accept we saw somewhere. Data accept. And the data response was, wow, so that's here. But this was not, so this is some kind of attachment process, and then after that, okay, so we found a packet that was from the router to our device, and it contains the operational data set. But yeah, let's continue this in the next video. Okay, so just jumping right back into it. Here, so this data request, so for the joining device, if it doesn't have all the network credentials, and if it just have the network key, then it makes a data request, and then basically here the data response contains all the sum of network data, and then active operational data set it contains, and then it provides it, and it even includes the key, which is very interesting because this device already have the key. But maybe it is possible that this mechanism can be used to change the key or something like this. Yeah, so this is exactly the same key, right? Yeah, that's the same key. Let's rerun this again. Let's wait. OT if config down, OT if config down. Then we clear the screens. We want to be these devices as ready as possible. So what we need is to reset this active data set to this one. So what we do is OT dataset commit active, and then OT dataset active is this one, and OT if config up, OT if config up. So let's start sniffing, and then we do is OT thread start, OT state. So currently it's detached. Currently still detached because it's trying to figure out if there is existing network. Now it's trying to connect. I don't know why, but there is no link accept. But I guess since the standard it's not so clear, maybe not all the time devices respond with link accept. That's why they do a parent request again, and then there is a data response which contains the network data, but this data response is, I guess, to announce that now I have created a network with the following information. the data response header is thread, and then here we have data request, a request typically containing a TLV request that indicates which TLVs are being requested, and data response, a response to data request containing TLV that were requested. TLV is not stored by respondent, not defined to be requested or silently ignored, not included in the response. But what is happening now? So this device is basically operational. If you look here, it is leader. So what we do is OT thread start. So we want our second device to start, and what we do is OT data set active. We check the data set continuously. Now we have received the data set, so let's stop somewhere. Okay, so child ID response, and now at this time it contains the active operational data set, which is interesting again. Last time it was a separate request. So from this you can see that this network, a lot of things can happen in a lot of different ways, and devices have some kind of fallbacks mechanisms and things like that. So now if you look here, our device did a link request. We did several link requests. After it saw the advertisement, or maybe that was not after it saw the advertisement, but it's just the way it's programmed, that it does some link requests and done some parent requests, and maybe some devices response to link requests, some devices response to parent requests. But in this case, it received a response to a parent request, and that was a parent response. And this parent response contained data about the leader, maybe some other information that then it used to request a child ID. It received a child ID, but maybe at some point, some cases it gets lost or whatever. But in this case, the child ID also contains the operational data set that the device then need. We already have the key. I don't know what happens if our device does not have the key, but if our device has the key, then I guess it can read this information. Let's go look at the security header. The security header is security field is explicit key with 4 octet, and yeah, I don't know how key is determined explicitly from the 4 octet. So if any of you know how this key is extracted, then let me know. But I think it's not just all the information contained in the packet, because then anyone would be able to listen here. So probably there is some input here from the network key which we have configured there, and from Wireshark it cannot decrypt it without that key. So this is why I think it is needed. But this is how they share the operational data set with the device if you just have the key. And yeah, this is how it used the mesh link establishment protocol. Power you can think of by the network key or some kind of encryption key, to then how it establishes link layer security. And then for MLE, link layer security is not needed. So I think almost all the MLE packets are then secured using this way, the way it is here now. And maybe some application layer protocols then are encrypted via link layer security, and we will have a look at that in the next videos. Thank you very much for watching, and I hope this video was not too much chaotic and you were able to learn something from this. See you in the next one.